So the other night, I spent, easily 20 minutes stubbornly arguing with a friend in this really dimly lit restaurant over my shirt.
Oh no. Let me guess. The classic navy blue versus black debate.
Exactly. We were literally holding my sleeve up to a candle.
Hmm.
But it really just highlights how, subjective and frankly chaotic human vision feels to you in the moment.
It really does. And what's funny is right around the time you were squinting at your shirt, scientists at Los Alamos National Laboratory were actually fixing the mathematical map for that exact kind of visual chaos.
Wait, fixing a mathematical map, what do you mean?
Yeah, they just finished up this century-old color theory. It was actually originally started by the physicist Erwin Schrödinger.
That guy. He did color theory too.
He did. And in the sources we're diving into today, we see that Schrödinger modeled human color perception as this sort of 3D cone.
Okay, a 3D cone with like absolute black where at the bottom tip, right?
Exactly. So he figured that if you take, say, a bright red apple and just dim the lights, the color just drops straight down a perfectly vertical line right to absolute black.
But wait, that doesn't actually make
No.
sense because if I turn down the lights on an apple, it doesn't just look, dark red. The shade itself actually shifts and gets kind of muddy.
Right, and that muddy shift is exactly where Schrödinger's perfectly straight lines basically fell apart.
So his math was just too perfect for our messy eyes.
Spot on. It's because of something called the Bezold Brücke effect. As the light drops, your eyes physically switch over from cone cells to rod cells.
Oh, and rods are the ones for night vision, but they only really see in grayscale, right?
Exactly. So during that cellular handoff, your actual perception of the hue warps heavily toward pure red or pure green or blue.
Okay, so if a straight line down to black doesn't actually work, how did the Los Alamos team fix the map?
Well, they realized you have to use curved paths, geodesics. But to calculate those, they had to move human vision into a non-Riemannian mathematical space.
Okay, hold on. You completely lost me at non-Riemannian space.
Yeah,
What does that even mean?
fair enough. Think of it like a map. On a flat paper map, the shortest distance between two cities is just a straight line.
Right, obviously.
But if you're hiking in the real world, and there's a massive steep mountain directly between those cities, walking over the peak takes a massive amount of effort.
Yeah, you would definitely just walk around it.
Exactly. The functionally shortest path for a human is to curve around the base. Non-Riemannian geometry maps that changing effort. The rules of distance actually warp depending on the terrain.
Oh, I get it now. So in vision, the mountain is like the extreme contrast between a bright sunny day and a dark room.
He nailed it. Human eyes experience diminishing returns.
Right. We notice contrast completely differently in bright sun versus moonlight. So a standard map just can't handle that dynamic shift.
Exactly, which is why that radically different non-Riemannian math is so crucial.
That makes a ton of sense. You need a map that adapts. And honestly, trying to map out dynamic, complex integrations reminds me of our sponsor, Silk.
Oh, totally.
Because if you are dealing with complex systems in your own business, you don't need to invent new math. Whether you need AI training, software development, or you're just trying to uncover where agents can make the most impact, you just need Silk. Check out embersilk.com for all your AI needs.
It's all about having the right tools. And going back to the Los Alamos team, they actually ran human experiments that proved this complex non-Riemannian space really works perfectly.
But so they tested this on real people.
They did. And even in this weird curving mathematical space, the shortest perceived path to a neutral gray axis is completely flawless.
Okay, but what does that mean for you and me? Like, how does this curving math change the tech we use every day?
Well, think about your phone screen when you walk out of a dark room and into glaring sunlight. Right now, screens just clumsily blast the backlight at you.
Oh yeah, and it always looks washed out or blinding.
Right, but with these new non-Riemannian algorithms, future digital displays and virtual reality headsets will seamlessly calibrate colors to match the exact curvature of human perception.
Wow, so it will be flawlessly tuned to our biology. That is such an optimistic vision for the future of tech.
It really is. It's a huge leap forward for human-computer interaction.
It is. But I had a sudden aha moment reading the sources. If color perception isn't linear, doesn't that completely break Thurstone's famous psychological model?
Oh, you caught that. Yes, it absolutely does. Thurstone's model assumes perceptions are just linearly added together, basically 1 + 1 = 2 in the brain.
Right, it's been the cornerstone for decades.
Yeah.
But if visual perception is fundamentally nonlinear, that changes everything.
Exactly. It suggests our broader cognitive processes might be nonlinear too. This could rewrite cognitive psychology entirely.
That is wild. proving why my shirt looks black in a dim restaurant could rewrite our understanding of the human mind.
It really could.
Yeah.
And it leaves you with this pretty provocative thought. If our vision relies on this complex math to navigate extreme contrasts, could our senses of touch and hearing secretly operate on the exact same non-Riemannian geometry?
Oh, wow. Universal mathematics for all our senses.
Mm.
That is deeply cool to think about.
It really makes you appreciate how incredible human biology is, you know?
Absolutely. Well, if you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.